All right. So just to complete what we were doing last time, um, we were taking a look at this cantilever beam with the Ritz method and the exact solution. So we said that since we need to satisfy these two conditions, these conditions are uh, no no transverse displacement at this point and no transverse rotation at this point. And on the right hand, there is no shear, no point shear, point load applied, and no external moment applied. So both of those quantities are zero. So given these two boundary conditions, these are the essential boundary conditions. That is what we need to satisfy in our Ritz approximation. So the approximation, one term approximation that we chose was the quadratic x square. And that just gave us a simple 1 cross 1 stiffness matrix, and you solve for that, and you see that up to a quadratic approximation, you can get this answer. And if you calculate the exact solution, all you need to do is to integrate this equation um, 3 times, so or 4 times, I guess, 4 times. And then at every stage of the integration, you can actually continue to impose all these boundary conditions. One common way that people do is just integrate it 4 times. You have 4 constants and try to solve. But that might be a little longer than this. So you can see that once you actually find the final answer, you will see that the exact solution is fourth order polynomial. So, and if you compare the tip displacement at x is equal to L from the Ritz method, we get 1 upon 12 this quantity, and from the exact solution we get 1 upon 8 this quantity. So the Ritz method is a lot stiffer if we choose only quadratic terms. If we choose only x square, then the Ritz method turns out to be quite stiff in comparison to the exact solution. So we can add obviously x cube to this term, then we'll have a 2 cross 2 stiffness matrix. If we add x4, then we'll have a 3 cross 3 stiffness matrix, and when we do that, we should recover the exact solution, because we know that anytime we use the Ritz method, if our shape function that we choose has the exact solution in it, then the finite element method or the Ritz method will find that exact solution. All right, so that was what we were talking about last time. Um, so if you take a look at the sheet that I handed you for today, the list of topics, um, so primarily we are going to have on this midterm this chapter 3 and whatever little bit we have covered of chapter 4 in beams and frames. So in this chapter also, I think there is not a whole lot of new conceptually. What we are doing is the exact same thing. You take your you should be comfortable with writing these governing equations. If I change the structure a little bit, then you should be able to find, let's say, instead of these types of pure uh, pure displacement or pure traction boundary conditions, if I give you something like that you had on your homework, you had a square plate on the same boundary, 1 degree of freedom is fixed in the vertical direction, and the other degree of freedom is free. So you should be able to write those kinds of hybrid boundary conditions. Um, Also, if you have maybe a plate sitting on um, a distributed spring, so you should be able to write the boundary conditions for those kinds of problems. Um, so in this case, we went over this also something called the Voigt notation, where you convert all these stresses in from the matrix notation to the vector notation. This came in handy later on, and this is also something that is important that you need to understand. What is the difference between plane stress and plane strain type of problems? Um, so in the plane stress problem, we assume that the cross thickness stresses are 0. So those kinds of problems are really when you have a thin plate. Similarly, for plane strain, we say that if you have some very long body, let's say a dam, no point and if you consider a cross section of that dam, then no point of that dam is going to move in the longitudinal direction. So displacements are all constrained to be in this plane, and that immediately means that the strain in the 3-3 direction is going to be 0. So those kinds of problems are called plane strain. And we saw that if you specialize your three-dimensional elasticity matrix using these two assumptions, you can write out a new constitutive law for this plane strain and the plane strain and plane stress cases. So so this is basically the sort of the strong form of the equations, and we had taken a look at two types of problems. One was the heat conduction problem, where I could specify some boundary temperature, some heat flux in the domain, and I could ask you what is the distribution of the temperature within the body. So the governing equations for those were given here. Now this is a scalar problem. What we are trying to do is find theta as a function of x. Theta is the temperature, it's a scalar. X is a vector, it's a position vector. So it's a scalar function of a vector variable. But all this equation is a scalar, there's only one equation in there. On the other hand, if you consider two-dimensional elasticity, there are this is a vector equation, so there are 2 degrees of freedom in this equation. And once again, to complete the problem, to complete the strong form, you need the governing equation and the boundary condition. And then after that, our method of weighted residuals is pretty straightforward, but you need to make sure that you can follow all these steps. If I change the governing equation a little bit, if I give you a little different governing equation, you should be able to do integration by parts in 2 and 3 dimensions. Okay. Using so there are 2 steps in this integration by parts. One is this product rule. So this was the product rule. If you find out if you want to integrate by parts this equation, then essentially what you have is this term is right here. So this term can be written as this term minus this term. And when you take the integral of that, you will get a boundary term, and to find out what this boundary term is, you need the divergence theorem. So those of you who are not that comfortable with the divergence theorem, take a look at Jelmsted's chapter 5. Okay, so in that we did this in 1 dimension, and you can go back and take a look at the chapter 2 from our notes. But how to do, if you want more details about how to do this boundary calculation for 2 dimensions and 3 dimensions, take a look at that chapter 5 from Jelmsted's book. But again, so this divergence theorem is nothing very tricky. In 1 dimension, what it boils down to is if you have some derivative of a function and you integrate it between 2 limits, essentially we are finding fb minus fa. In 1 dimension, this is what is called the fundamental theorem of calculus. And in 2 dimensions and 3 dimensions, this is what we use or what we call a divergence theorem. So it's not that complicated, but you need to know how to work with all these terms. So how many of you were able to follow this initial notation that we wrote? How many of you were not able to follow the? Okay, nobody's going to raise their hand, I guess. But yeah, if you are having trouble with that, that's why I think what I did here was wrote out this entire quantity in terms of 1, 2, and all that. So you can make sure that if you're not comfortable with the initial notation, write out all the terms and do the product rule on each on each of those terms. Um, so finally, we get our weak form, and this is essentially what we discretize and implement on the computer. So we also saw that for 2 dimensions and 3 dimensions, we had all these different types of discretization techniques. Um, you can break it up into a regular rectangles, and this you can break it up into uh, arbitrary triangles. And this technique is called Delaunay triangulation. So whenever you have a convex domain, what convex domain means is that you don't have any re-entrant type of curves on the boundary. So if your domain is convex, then you can always use this Delaunay triangulation to break it up into different parts. And that's how I was I was generating all those input files for your homework problems. So, so essentially, uh, here is where you start to build in the approximation. Up until now, you had the strong form of, or the governing equations. You find the weak form, there's no approximation. You discretize the domain, divide it into small parts, and you divide your integral into a sum over all these parts. Even then, there is no approximation. Once you assume that your solution within an element is going to be, let's say, linear, that's when you make the approximation. So I think a lot of people actually ask what is the finite element method. So and one common answer is that, well, you divide your domain into different parts and analyze those parts and assemble them together. But that is not really what we are doing. Essentially what we're doing is we divide our domain into all these small parts, but then we assume that within each part the solution is going to follow a linear variation, let's say, or a quadratic variation. And that allows us to assemble the entire global solution. If we say that we divide our domain into these many parts, and within each part the solution is going to be linear or quadratic, and then we assemble the whole thing together, that is what a good way to describe what a finite element is to somebody who doesn't have that background. So all right, so we divide this up into different elements, uh, and finally you introduce your finite element approximation. So the first type of element that we saw was this 3-noded triangle, and this is something that you should all be comfortable with. If I give you the nodes of the triangle, then you should be able to find out all the shape functions, the stiffness matrix, and all that. So I don't think many people had trouble with. How many of you did not get the CST code from homework 5, problem 3 to work? Okay, everybody got it work. Yeah, that's what I sort of remember from the homework. Um, and this is also important. Why does this work? Because this is an H1 space over all this domain. So if you assemble the shape functions for a particular node, they look like this tent type of shape function, which means that the function itself is continuous. And if I give you a picture where with some shape functions for different elements, and I ask you to assemble them and ask you whether this is a valid finite element discretization or not, you should be able to conclude that simply from the continuity. All we need is on each and every edge, that function needs to be continuous. So if the function is continuous in in 2 dimensions, it is a valid function to choose for your finite element approximation. And we also saw that this approximation, whatever variable you're solving for, in this case it's temperature or displacement, that can be written out as a matrix times degrees of freedom. Similarly, you have the strains, that is the derivative matrix times the same degrees of freedom. All right, so in this triangle, the type of questions that I might ask you is, can you prove that the sum of the shape functions at any point is 1? How would you do that? So I give you the 3 coordinates of the triangle, and if I ask you that at a 4th point somewhere in the triangle, can you show that sum of the shape functions is 1? So uh, you would have to do some calculations like this, write out the 3 shape functions, sum them up, and you'll see that all the x and the y coefficients cancel out. And you'll see that what you will get is 1 over 2 delta times a1 plus a2 plus a3. So a1 plus a2 plus a3 is actually exactly 2 delta, and that's how you show sum of shape functions at a point is 1. So similarly, assembly, hopefully this should not be too complicated. If you have different number of degrees of freedom at a node, then you should be able to assemble. If I give you, or if I ask you something like a mixed problem where you have part of the mesh is rectangular, part of the mesh is triangular, and if I ask you to assemble the equation for one node, you should be able to do that. So the couple of examples that we took a look at in this were, so the same thing for elasticity problem, you can derive the weak form. All those matrices have a little bit different form, and this is when you have 2 degrees of freedom per node. Okay. So one critical thing is the integrals for the domain, either the K matrix or the F vector. For the triangular elements, you can find those integrals exactly for the CST element, and so those are the types of problems that I could give you on the exam. And I think in the notes what we did was a constant body force or a constant traction on the edge. So I could change that a little bit. I could give you a distribution of the body force over the domain, or I could say that the traction on this edge is not actually constant, maybe it is linear. And how does your force vector change? How would you do that? So something like this. Let's say you have this triangular element, and if I give you a traction that is acting in this way, how would you find the body force, the element force vector? What is the expression that we get from the weak form? N transpose, so integral over the domain first of N matrix transpose any body force if it is there, and this is the integral over the domain, plus integral over the boundary N transpose F, or let's say traction T, Tn dl. So let's say these are the 3 nodes, 1, 2, 3. We have the coordinates of these, and we also have the traction vector Tx, Ty, and this traction vector is a function of a variable s that goes from here. So this Tx is a function of s, ty is a function of s, and it is a linear function. It starts from 0, so it is something like a1s, this is b1s. And what is the size of this matrix? So the first term, let's say the boundary force is 0, the body force is 0. What is the size of this matrix? N transpose. What is the size of n first? How many shape functions do we have? We have 3 shape functions for the 3 nodes, right? So n matrix is 2 cross 6, n transpose is 6 cross 2. And that would look something like this: n1, n1, n2, n2, n3, n3. And we will have this tx as a function of s, ty as a function of s here. So when you multiply these two out, what you will get is a 6 cross 1 vector, which is the same size as your element force vector. And since this dl is the same as ds, essentially this calculation should not be that difficult. So any terms here, obviously there are these 0 terms, and this will lead to some 6 cross 1 f element vector. So can you definitely say that any of these terms will be 0? None of these terms will be 0? How about the shape function for node 1? The shape function for node 1 is going to be 0 all along this edge, right? So in this integral, n transpose, both these terms will be 0. All along this edge, this n1 will be 0. So this will be 0, this will be 0. So essentially, that's how you should, even on the exam, you should try to eliminate as many terms as possible beforehand. So in the last midterm, I gave you a 3 cross 3 3-noded linear line element, but I think one column and one row you could have eliminated just by the boundary conditions. So you needed to integrate only a 2 cross 2 matrix. So in this case also, all you need to do is integrate these, actually only this term and this term. So so try to see what are these shortcuts that you could take in the process. Okay, so that could be one type of problem. Some more examples that we did: integral for the K matrix. And this was basically the outline of this entire process. You start with the governing equations, write the weak form, discretize, approximate your finite element method, do your assembly, and enforce boundary conditions. And something else that we saw was the inclined boundary condition and the symmetry condition. So if I give you some problem, maybe it's some domain where you can use symmetry, so you have to watch out for that too. All right, so other than this T3 element, we took a look at this Q4, and the isoparametric formulation is also a big important part of this exam. So you should be comfortable with how this isoparametric map works. How do we construct the shape functions? So this was also a problem that was on your homework 5. see what I wanted to say in this. Okay. Right. So the general Q4 element. Make sure you understand this map. How does this map work? So essentially, the isoparametric map is right here. We are expressing the coordinates of a point in the actual element versus the corresponding point in the parent element. And the couple of important things to keep in mind here is that when we assemble or when we try to find the stiffness matrix for the element, what we need is these quantities, this B, which is derivatives with respect to x and y. And in order to calculate these derivatives with respect to x and y, we had to work with something called the Jacobian. So make sure you go through this derivation. Make sure you understand what is the physical meaning of this Jacobian. So, okay, let me ask you this. If I have a perfectly square, that's my parent element, and if I deform or if I map it to something like this, to a parallelogram, where uh, what do you think? Is the Jacobian going to be constant for this or not? What does the Jacobian represent? It, sorry, change in the domain. So point-wise, essentially, if you have a square plate and if you deform that, you can imagine that the stress and the strain at different points within this actual element, when you deform this square element to this, will be the same. If you have some distortion, maybe if your actual element is not a parallelogram, if it is something like this, then you can see pretty much that in some of these regions, the stretching of that element is much larger. And whereas this angle remains close to 90 degrees, so the value of the Jacobian will be different at different points. And I could give you a point, give you the 4 coordinates, and ask you to calculate the Jacobian, similar to your homework 6. So what if I simply take this this square and rotate it to a new position? Let's say here. What would be Jacobian? The Jacobian matrix. What would that be? What would be the determinant of the Jacobian? Determinant of the Jacobian would be 1. So what would be this Jacobian matrix? Sorry, 1? You're saying something like this: 1, minus 1, minus 1, 1. So yeah, you need to take into account the rotations. Basically, if you remember, Jacobian matrix is dx over dc, dx over d eta, um, and dy over dc, dy over d eta. So if all I'm doing is taking a square, rotating it to a new position, then the xy is a linear function of c eta, which means that each of these values will be some constant. When you take the determinant of that, it will come out to be whatever this is. The determinant of that Jacobian will turn out to be 1. So these sort of physical interpretations or physical meaning of these terms, you should make sure you understand, so that that will help you in making judgments whether and sort of expecting what the final answer should be. Okay. So after mapped elements, we talked about reduced and full integration, or the numerical integration. This is also so I obviously don't expect you to do a whole lot of for loop kind of calculation by hand. Some of the homeworks and problems, homework 6, they were better done by MATLAB. So if I do give you something like this, then I'll give you enough data, and I can maybe ask you what is the contribution of one of those Gauss points to a force element vector. Okay, so those kinds of questions I could ask you. All right, so then we took a look at what is the minimum condition, appropriate order of quadrature. So let's say I have a parent Q4 element. This is going to be mapped. This is going to be mapped to a actual element. How do I decide what is the minimum order of quadrature? What is the minimum number of Gauss points required for convergence? What is the test that we use? Sorry? Yeah, number of nodes. It is related to that, but the test that we use is that it has to be able to reproduce a state of constant stress. So what that means is, actually you can show that if uh, if this condition is to be satisfied, then what you need is that you need to be able to integrate a Jacobian exactly. So I think somewhere was this, right? So if the stress state is constant, as you take in the limit, you can pull this out of the integral. What you will be left with is this type of thing, and this thing you need to be able to integrate exactly. And to integrate this domain integral exactly, what you are essentially doing is integrating the determinant of the Jacobian. And to do this, we found that for the Q4 elements, Jacobian is linear in C and eta. Therefore, the determinant of Jacobian would be quadratic. Where is that? So the determinant of that Jacobian, I think I mentioned that somewhere on the notes. So anyway, I guess in this case you can see for Q9, the Jacobian turns out to be C times eta square, and all these terms, their proportionality order is given here. So if you calculate the determinant of this Jacobian, that turns out to be C to the power 3, eta to the power 3, and that means that you can use reduced integration, which is of 2 cross 2 order. So I could give you something like a different type of a element and ask you what is the minimum order of quadrature required. So what would be the minimum order of quadrature required for, let's say, if you have 3 nodes in the C and eta direction each? If you have 3 nodes in each of those, then all your shape functions, they are going to be cubic in C and eta. Your dx over dx is going to be C square eta cube. This would be C cube eta square, which and the total would be order 5, right? So what order of Gauss quadrature does a polynomial, what order of Gauss quadrature would be required to integrate a 5th degree polynomial? 3 Gauss points, because it is 2n minus 1. Does that ring a bell? So yeah, make sure you understand what is the minimum Gauss quadrature required. So if you have 2 points, you can integrate quadratic. If you have 3 points, you can integrate up to 5th degree polynomial. So, and that is what is called reduced integration, and we saw some of the consequences of that. Um, we saw that if we just use one Gauss quadrature, the computation will be fast. And if you calculate the stresses at this point, so hopefully this is you should have done for your homework 6. You did your integrals using full integration, but then when you calculated stresses, we calculated the stresses at the Gauss point. I think and then we talked about some of these higher order elements. Um, these are higher order rectangular elements. The hierarchical elements. So in the rectangular elements, we had 2 types of families of higher order elements. One is the Lagrange family, where you keep on adding nodes in both the directions uniformly, 3 nodes in C and eta. But the Serendipity family is a little more tricky, and you make sure you understand how you can construct a new element using this serendipity idea. So, and we also talked about how these transition elements can be constructed using this serendipity idea. If you want to connect a Q4 with a Q9 or a Q8, you need to construct this new 5 node element. And the reason that you need to do that is to make sure that on the edge your shape function remains continuous. If on the edge the shape function is not continuous, then that is not a valid formulation. Okay. There was somewhere we did area coordinates. That is obviously important. I guess here, right? So higher order triangular elements, the terms that are that we are approximating with these higher order triangular elements, how to construct the shape functions using these area coordinates, that you should be familiar with. I could maybe ask you to find a particular term in the stiffness matrix, those kinds of things. And then some of the rest of these topics, convergence and the variational principles and constraints, those are maybe just for general knowledge. I could ask you maybe some short question on that. So that's sort of the, and then we've already talked about beams and frames a little recently, so let me not go over that too much. All right, so for the homework 5 in this problem, I think everybody pretty much got it right. Maybe you made a small calculation mistake somewhere, but most of you got this right. In this one, this is a little bit important that you should have seen that this is a constant traction in the x and the y direction. You can actually calculate the exact solution for this problem. And if you take a look at the solution that I posted, in this case, this is just deriving the weak form. Substitute your finite element approximation, and you should also be able to see that all the 4 stiffness matrices for all these 4 elements would turn out to be the exact same stiffness matrix. So I actually coded this up using the same code that I provided you. Has anybody taken a look at this? All these codes? So now this code has all these elements. It has the T3 element, it has the quadratic T6 element, and it has the isoparametric Q4 element in there. So you can use any combination of those elements as long as you construct your mesh in such a way that your boundary matches up. So let me briefly go over this T3 element. The code for this was really not that not too complicated. if somebody gives you the coordinates x1, x2, x3, and y1, y2, y3, we saw that the B matrix will be constants. This is a constant strain triangle. And then some people, I think, made a mistake with this differentiating between the absolute area versus the determinant. So the signed area, this area has a sign. If I told you that if you don't choose your elements in the counterclockwise direction, this sign will turn out to be negative. So you needed to use this absolute area for only for the final point where you multiply your B transpose dB with the integral. So okay, let me ask you this. How many elements would I require for this problem to get the exact solution? We used 4 elements in this problem. And the exact solution is that the strain and the stresses are uniform throughout this element. So if you use even just one constant strain triangle, you will get the exact solution. So so this problem required you to transform your degrees of freedom from your 5, 6, and 11, 12 to the prime coordinates. And but one another thing that I should probably mention here is that some of you who did not get the exact answer ended up trying to justify that their answer was correct, which is a little bit dangerous in finite elements. You should be able to judge when the program is not giving you the right answers. So anyway, so these kinds of questions also can be there. If I give you an exact solution and ask you how many finite elements are required to get the exact solution, you should be able to judge that the state of stress and state of strain in this problem is uniform throughout the domain. So all you need is one CST element, because that can reproduce a state of constant stress and strain. So finally, for this homework 6, this was all these 6 parts were a little bit lengthy to do by hand, but if you feel more comfortable making sure that you understand each of the steps, then I saw that few people did it by hand, which is fine. But obviously MATLAB will be much more convenient in this case. And the same problem with a T6 element. So no surprises there. A T6 element can actually is a higher order element. One T6 element is sufficient to get the exact solution. On this problem 3, some people were using sims in your, like the symbolic MATLAB. That was a common usage, but obviously if you use sims, you might have noticed that the speed of your program is going to deteriorate very quickly. So try to run some of these problems. I've given you this code and all these input files, also some of the plates. So this is the problem with the square plate half symmetry with the T6 element. In the solutions I've given you all these problems. Try to run these problems. Go through the code using the debugger. How many of you are using the debugger? Okay, so that's good. Anytime you go through the steps and you don't see why it is computing what it is computing, you need to make sure go back to the notes and take a look at what we were doing there. So I guess from homework 6 there was, for the T6 element, the integration, right? If you go to the T6 element routine that I posted, it starts out pretty similar to the T3 element. You have all these three main node locations. Those are the corner node locations for the T3. These are the corner node locations for the underlying T3. You can calculate the same area coordinates. Those are not going to change because that underlying T3 and the additional nodes that we add in T6, they're all equally spaced. So the underlying area coordinates for the T6 remain the same. But in this subroutine, what I did was I used a triangular quadrature. So this is something similar to Gauss quadrature. And if you go to your book by Zienkiewicz, it gives you, just like the Gauss quadrature formulas, it gives you the quadrature formulas for triangular elements. So essentially what it is saying is calculate the value of whatever integrand that you have at these 3 points, A, B, and C. And that's what I did in this case. You have these triangular or area coordinates, L1, L2, L3, and you can see that once you calculate your integrand at this point, you can integrate anything that has quadratic order. So if you can see this. So if you use this 3-point rule for the triangular elements, I think a lot of you did your integrations in X and Y, and you could do that only because this triangle was oriented along XY axis. So if this triangle was not oriented along the XY axis, you would have had to transform your integral. And some of you tried to use those factorial formulas that I gave you, but the correct way to use those factorial formulas would be to first derive that 2 cross 2 matrix that I told you about. Derive that 2 cross 2 matrix for in the hint that I gave you, and then try to assemble that 2 cross 2 matrix in that for this element, which would be 12 cross 12. But in this case, all you needed to do was calculate your B matrix. Calculate your B matrix at these 3 points. This is A, B, and C, and just use the sum. So this is something very similar to what we did in Q4. But instead of the approximation, this is an exact integral. And it is an exact integral because we know that the integrand in this case, that is a quadratic polynomial. So why is this integrand a quadratic polynomial? What would be the terms in the B matrix? Okay. So the terms in the B matrix are all these. These are the shape functions, derivatives with respect to x, y. And each of those terms is going to be linear in L1 or L2 and L3. When you take B transpose dB, you will get something that is quadratic. And looking at this table, the error is going to be of the order of cubic. So any quadratic function of L1, L2, L3, you can integrate with these 3 points. And there was also, I guess, somebody posted that if you have constant body force, all the load goes to these 3 points. So none of the corner nodes will take any load. And the reason is that these 3 points actually form form what are called quadrature points for triangular elements. So so you can assemble your stiffness matrix for the T6 element using this. So yeah, basically that's you have all the codes. Take a look at them, and then if you have any other questions, we can meet again on Monday. If you have any other, also I think on this handout, I gave you some references and exercises. So pretty much chapters 8, 9, and 11 from the Reddy's book, and chapters 2 through 5 on Zienkiewicz and Taylor. Take a look at the exercises in the back of that chapter, and we have not covered all of those chapters. So make a judgment whether this is on the syllabus or not using the notes. All right, so see you guys Monday.